Oh boy, we're almost done with circular motion.
Can we just finish circular motion today and then get out early? Pretty please.
All right, so we were talking about, we were talking about a new form of acceleration based off the non-uniform circular motion. And you notice that we have these two components for this acceleration, which you have your tangential acceleration and your radial acceleration. So to kind of finish up this idea, we've been working with the magnitude of vectors. So do you remember? So if we had originally we had an acceleration where you had that. How would you find the magnitude of the acceleration produced by non-uniform circular motion? It's real simple. No, it's the magnitude of the acceleration vector that's produced by the non-uniform circular motion. This was the way we were finding magnitudes. What do we do now? Kind of. It's still the components. So since your components are radial and tangential, your magnitude of this acceleration is going to be the square of radial plus the square of tangential, and then the square root of the whole thing.
So basically almost the same.
Yeah, pretty much exactly the same. You're just putting in the proper components. Certain things that don't change for non-uniform circular motion. We still have that definition for radial acceleration. Let's see, with non-uniform circular motion, we also still have V equals R negative. So these definitions are not going to change. Okay. So here we go. Roller coaster has a vertical loop radius 20
I'm
meters.
not done.
What?
You go back up for 1 sec.
Sorry, actually. We're just do it, we both just threw something at it.
Yeah,
I would have the same reaction, what? Sorry.
It didn't seem like that much to write down.
I do, yeah.
I wrote like the wrong.
Dana has to
Oh.
really squint at it though.
I have to like.
I have a
put my
real
camera
question.
And look.
What letter is this one? That O we have?
Not just a cursive.
Yeah, right?
I mean, it could be a cursive O, it could be trying to get out a lowercase sigma, but
That's right.
that's not quite right.
A
Why is that
lowercase
not quite
sigma.
right?
That's the one that's like, is there more slides?
Yes,
Yes,
Like a lot more on circular?
no, there's like 8 more.
see, that's sigma.
It only goes down to 43. That's sigma.
Oh,
Well, what
that's
do you mean by
close.
lowercase sigma though?
I don't know, it's close to that.
That's just how I draw my signals, I just turn them around.
Oh,
You know, there
okay.
was a lowercase sigma.
Yep. So again, roller coaster,
Sigma bond.
vertical loop, 20 centimeters. The speed of the roller coaster at the bottom of the loop is 25 meters per second. What is the normal force exerted on the car by the track in terms of the car's weight? Okay, so imagine you're going to have this loop. The roller coaster car is going around the loop. You're going to have the gravitational force of the car. You're going to have radial acceleration and your normal force. So as per usual, radial forces. Oh, that's going to be a normal force. G equals AC or AR, centripetal, radial, remember they're the same thing. Never mind. Centripetal is radial towards the center of the circle. Centrifugal is radial outwards.
And what letter do you use for that?
For centrifugal, we'll probably just use R. So centripetal is going to be radial towards the center of your circular motion. Centrifugal is going to be radial outwards, because you notice here that your mass times gravity is a radial force. And it's going to be a force going outwards from the loop. Now, what signs are these going to have? Yes, why? Not necessarily. It's pointing away from the center of curvature.
Yeah.
Yep.
Yeah.
Yeah. Okay. Coincidence does not equal causation.
What am I wrong?
In this case, no. If I move the car a little bit, you would be. So, for example, the mass times gravity, if the car was at the top of the loop,
Well, then, yeah, so.
Gravity's still going.
it'd still be going down,
Yeah.
but MG would be positive.
True. Oh.
Normal force is towards the interior of the curvature. MG is outward from the curvature. And the centripetal acceleration is inwards towards the center of curvature. Okay, so now we can say normal force that's what says radial. Remember, radial is a generalized term.
Oh, that's
Well, why does it,
C is centripetal.
why don't we include that in the summary?
It's good. It's just, at this point, centripetal and radial, you can interchange them.
Oh, so that's basically what you see.
Yeah.
Okay.
So but eventually, when we talk about centrifugal force, you'll have you'll have two radial forces, inwards, which is centripetal, outwards, which is centrifugal.
And outward, we just keep going.
Yeah. So you see that the normal force is actually going to increase due to the acceleration. So we don't quite know what that acceleration is, so we have to. Hang on. It's a step the textbook did. I'm just not sure we need it. Now let's try this. So AC is going to be, remember, E squared over R, G. So when you put your numbers in, so, oh, that's why. Okay. You see, the question says, what is the normal force exerted on the car by the track in terms of the car's weight, mg? So we want a number multiplied by mg. We're not actually going to calculate in mg. The answer has to be some number, some multiple of the weight, the gravitational force of the car. Okay, so that's why the book took this step. If I'm just gonna put in numbers. Okay, so what we're gonna say then, so this is gonna equal M. You see the little trick there again? Multiply by 1. G over G is 1. Mhm. Why is this the case? Why is that true? Yeah, you could divide out G over G. So now we're going to be able to pull out. Well, they equal each other because G over G is 1.
He just made that up.
I did not just make it up.
But like essentially, like he just made up. Like
Oh,
like you
you're
could
just
put
writing
any,
that so I know.
like you could put any constant over there as long as you're saying to one.
No, I got that part. I just thought we were like continuing down with this equation. So I was like, why are you equaling it to AC? Like, why did you just take that out?
No, I'm just showing you that AC can become AC times G over G.
That makes more sense.
Because I want to pull out the G, we're going to end up with a number multiplied by the weight of the car. So we want to figure out what this, what the normal force is as a multiple of that weight. And so we have that. Now we can put in the AC equals V squared over R. Okay, now we can calculate the normal force. Then what you end up with is the normal force is about 4.19 times the weight of the car. So you can get an idea of how much extra force that centripetal acceleration is going to put on the car. You feel this on a roller coaster if you weren't too busy fixing the whiplash that it gave you previously.
I love
So if it goes upside down, does that change?
Oh yeah, if it goes upside down, you're still going to have a centripetal acceleration. However, your weight's pointing in a different direction this time. All right, the last little bit from this chapter, angular acceleration. Now, we've been talking about linear accelerations when referring to angular, like rotational motion, but now we have to talk about acceleration going around the circle.
Remind me what the W is again.
Omega, yeah, that's angular speed or angular velocity. Radians per second. So as you see, our angular acceleration is going to be the rate of change of angular velocity. And so we can translate then that into a linear acceleration. Remember that our linear acceleration is delta V over delta T. But then, of course, your V is R omega. So then that becomes R, and then again, the rate of change of your angular velocity. And so your linear acceleration now becomes R alpha, just like your linear velocity was R omega.
Is the alpha a new thing or did I just forget?
Well, no, that's your angular acceleration. So we're using, just, different symbols for angular motion. And you'll see why here in a few slides. Okay, so let's think about this. So let's say let's see, I'm going to try to draw this. I think it's right center. So just put an XY axis over that. And let's say we draw that one there. And draw that one there. You see it speeds up, so now we're getting an even bigger angle. And these are all measured at time 1, 2, 3. And so we could say then so we have the 3 angles that we're looking at. So we can start looking at these different velocities. Number 1 is going to be theta 2 minus theta 1. T2 minus T1. So we're going to get that first angular velocity between time 1 and 2. Then you say that omega 2, that's going to be theta 3, and theta 2. And omega 2 does not equal omega 1. These angular velocities are different. So what we know then is we have an acceleration alpha, and that's going to be omega 2 minus omega 1. And the acceleration is really prevalent between T3 and T2. And so you can see the basis of the delta omega over delta T. So that's really the idea of where it comes from. As you're going around the circle, you're just going around faster and faster and faster.
So why did you do time 3 and 2 instead of 3 and 1?
Because when you took time 1 and 2, that's just your first velocity. Now you're looking at what happens as you go from time 2 to time 3. So omega 1 is from T1 to T2. And then your omega 2 goes between T2 and T3, but that's where you're able to calculate your acceleration. Because without T3, you just have a single angular velocity that exists between T1 and T2. So then the question is, if you're solving problems with this, what are the units of angular acceleration? Close. What? Squared. Radians per second squared. So just like linear acceleration is meters per second squared, same idea here. And we can get to the other theorem that we had up there. You can say, well, if we go back to our idea, let's take a look here. Let's say we have you know, let's call this position T1, this position T2. Then at each one of these positions, we're going to have two different velocities. At this point, our tangential acceleration rate of change of velocity, you can call it, you can make this a scalar equation. And don't forget, this is tangential velocity. What we know is r times omega, so whatever that radius is. So you think of that, you have a radius r. So when we put that into this equation, so if you were to move that delta to the inside, which is r changing? If you're going around a circle, is r going to change? No. So what you're going to get is r delta omega t gives you r, which we now know from above is r times alpha. So you get very similar equations for both your angular speed and your angular acceleration. Your tangential velocity is r times omega, which is your angular velocity. Your tangential acceleration is r times alpha, which is your angular acceleration. And what this inevitably leads us to is now we have two complete sets of kinematic equations that we can use. On the left, you see the kinematics you've been using for linear calculations. On the right, now you have the same kinematic equations, but for angular motion. They're the same equations, you just have to put in the right symbols. But by the time we were getting near the end of angular acceleration, I thought that this was pretty pertinent. Now let's think about this. So the London Eye, you know that gigantic Ferris wheel in London? Let's see how cultured everyone is, how well. How do you pronounce that river? Bank of the, who said it? The Thames. Yeah.
No, we gotta pronounce the
Yeah.
Thames.
Yeah, I know. If you go to London, and you say Thames, they will have a tizzy.
I think they'd have a tizzy no matter what.
Yeah. Well, not unless, I mean, if you're in a place where there's soccer hooligans,
Yeah.
they're probably a little more laid back than you are. So, at its cruising angular speed, it takes 30 minutes to make one complete revolution. Let's see. Suppose it takes 20 seconds to bring the wheel from rest to its cruising speed. And the angular acceleration is constant during startup. So first off, what is the angular acceleration of the wheel during startup? Okay, let's see if we can figure that out. So the angular acceleration has to be in units of what? Radians per second squared. So First thing I'm gonna do when I translate this, that's gonna become 1800 seconds. Now, I'm going to end up using that. We use that kinematic equation. So I need an angular speed, I need the angular speed of its cruising speed. How do I get that? So one revolution is how many radians? It takes 1800 seconds to make that revolution. Oh, crap, someone was on that huge Ferris wheel. It took 18 seconds to make the revolution. That'd be a bad day. So what you end up with so now you have the angular velocity at the cruising speed. Now, which part of this kinematic equation becomes zero? The initial, because it starts from rest. Okay, so I'm going to have negative f alpha t alpha. It's going to equal negative f over delta t, which is going to be your 0.00349 radians per second over what? No, not 1800.
20 seconds.
20 seconds. That's how long it takes to get to cruising speed. Angular acceleration in this case is going to be 1.75 10 to the negative fourth radians per second squared. So not too bad if you know what you're looking at in the problem.
That was all for A.
That was really short though.
Yeah, I know. I was just wondering if that.
Okay, yeah. I thought you were saying all of that?
No, I can see how.
So that's part A. Part B, what is the angular displacement during startup? First off, you have to ask yourself, what is angular displacement going to look like? What is its symbol?
Change in S.
We're after delta theta. So I look at my kinematics. So you can think of like your delta theta, you can think of it as your delta x or delta y. Now, I chose this one, because again, I can make that 0.
Did you use this at one time?
Probably, yeah.
Make the animation.
There we go. So now we have Delta theta is going to come out to be. Out of all of that, what do you think the unit on delta theta is? Radians. Now you could go ahead and translate this. That turns out to be about 1.99 degrees. But the answer is in radians.
Wait, 1 radian is 1.1 degrees or that?
No, like this 0.348 radians is about 1.99 degrees. Because you remember that two ways you could do it is 360 degrees is 2 pi radians, that's a conversion. Or I used 180 degrees as pi radians. So you could take that number divided by pi, multiply it by 180, and you have degrees. Okay, so we've had so much fun on angular motion. Let's talk about something everyone loves to talk about. Conservation of energy, but we're going to get to the concept of work. Now you're going to notice something you probably already know just by intuition, that work is absolutely horrible because according to physics, work cannot happen without force. So one must be forced in order for work to occur.
That's why I can't.
If our head tweaks just over 4 and 5.
Yeah, it's just going to be over 4 and 5 because I don't have the energy to make a video for Monday. So
Yeah. Oh, darn it.
You're so
don't say that just yet. You're going to have an assignment today.
But we love you.
You mean an
Not
assignment for
making
next
us
week?
watch a
Yeah,
video.
you're going to get a new one today.
Oh, but like
When is it due?
So like today, so we do next Friday.
Okay.
So like every week.
Mhm.
What do we have? Are you gonna give
Can
us
I just-
one for over break?
Yeah, are you gonna have one for midterm?
It stops right here.
No.
I just didn't know if you're
Oh,
gonna
right.
have one.
Since we
I
all
don't know.
have
I haven't decided.
Okay.
Because what, we'll have lecture Wednesday.
No, we have.
Scholastic Day Wednesday.
Just have
No,
lecture
no,
That's
Friday.
no.
last 6 days after
No,
midterm break.
I mean like next Wednesday
Yeah.
and next Friday, so whatever would be over that.
Yeah, well, because I mean, there'll still be pretty enough angular motion for you to do, and whatever we get through this. So,
Oh, yes.
so the law of conservation of energy. The universe will end with the same amount of energy it began with. So in any system, initial energy equals the final energy. Which is kind of funny because you'll see some systems where you calculate, for example, the internal energy of the system and the initial is greater than the final. That's internal energy. Like if you're pushing a box along the ground, you can find those differences of energy, but then the question is the energy that should be there, where did it go? We'll learn that through what's called dissipative forces. Just a question, what do you think a dissipative force is?
Friction
Friction, that's a good one. So energy leaves the system how?
through heat.
Heat. So that's just an example. So in the end, your total energy does end up being the same. Your system can lose some energy due to dissipative forces, but the total energy of the universe is the same. Okay, work done by constant force. So let's think about this. Let's say we have a box. It starts here. We push it. With the force, and it ends up. That's close. It ends up over here. Okay, now we also know that this box has moved through a distance d. The work done, and we'll do this more generally, but the work done, so work is force applied across a distance. So how do you think you set this up? Force applied across a distance.
Like. Force.
Force multiplied by the distance. So let's say you had a force, 100 newtons, and D is 2 meters. That would be 100 newtons. That's 2 meters. It's 200, and we have a new unit. 200 Newton meters is a Newton meter. It's the unit of energy. So the work is energy applied across a distance. So the force supplies energy, the object moves. What is the unit of energy? It's joules. The Newton meter is the joule. But let's talk about work when the force is applied. When the force is applied at an angle. So we're going to get a brand new operation for our vectors. We've been doing vector addition. We've been doing vector subtraction. Now you're going to do vector multiplication. And in particular, work is going to be called the dot product or the scalar product. However, there are two different types of vector multiplication. When we get to torque, you're going to see the vector product or the cross product. So why do you think this one is called the scalar product? It doesn't have direction. It's going to produce a magnitude. It's going to produce a number. And that number can even be positive or negative. It gives you a sense of direction, but the number itself does not have direction. It's just a magnitude. Okay, so I'm going to take the same idea here. This box was moved. By a force at an angle. And it's going to be moved across the displacement. Delta R. And here, theta. And of course, we remember they're along here. So one thing you can start to think about is the portion of the force that's going to move the box is that portion of the force that is in the same direction as motion. So what is that component going to be? So it's the x component, and so it's what? No, what's it?
So you're talking about a force, right?
Yeah, what component is it? How do you write the component? Fx equals what?
Cosine.
Yeah, there you go.
I mean, it technically was right.
F cosine of theta. So that is the portion of that force that's in the same direction as motion. Okay, so now if we think about work done, we're going to have the force that's moving the box, F cosine theta, the displacement, delta R. You end up with this equation F delta R cosine of theta. And it just so happens that we've ended up on one of the definitions of the dot product. So now we can start talking about it. This is the generalized form of what work looks like, F dot dr, F dot delta R. Sorry, not dr, we're not working with differentials. So, two ways you can look at this. Let's say I have A dot B. The first way you do this, AX times BX plus AY and BY. We're going to multiply the components and add it together. So, for example, if we had, it's going to be 2i hat plus 3j hat, B is 2i hat plus 4j hat. And your A dot B, that's going to equal 2 times 2 plus 3 times 4, and that's going to give you the number 16. So you see the dot product is going to end up in a scalar quantity. And so just like this, one of the definitions for work then F dot delta R, we're going to have Fx to Rx plus Fy to Ry. So that's one way, that's one very legitimate way to solve the dot product. But like we said, the other way to look at it, so let's say we have vector A, vector B, and then here, theta, another definition for the dot product magnitude of the force, magnitude of the displacement, cosine of the angle between the two vectors. So if you go back up to where the box was being pulled or pushed, or pulled in this case, by a force that's not parallel, well, the delta R is going to be parallel. So let's just look at that. You see how the delta R, not parallel, is horizontal? And then the F makes an angle theta with the horizontal. So you could do F delta R cosine of that angle theta that F makes with the horizontal. So do you see how that F also makes that angle theta with delta R? So this is a basic insight. This is a basic beginning of how the dot product is done and what the energy of work actually is. There's 1 minute left, so there's just not enough time to get through anything else. So this chapter is going to be work energy. I can tell you from past years, for some people, the kinematics equations and kinematics is really difficult. They define with work energy. For other people, they get really great with kinematics and work energy is awful. For some people, they did both really well.
I think I'm gonna do both really awful, personally.
That doesn't happen very often.
Yes.